Welcome to this week's video session in which we introduce the stochastic integral. For the reading material we have chapter 2 in our textbook by Mikosh and additionally recommended two references by Laura and by Kalin, each dealing with stochastic calculus. So before we can speak about the stochastic integral, let us remind us about the definitions of the integral. So we have the so-called Riemann integral, which is defined in terms of Riemann sums. So we have a function and we want to measure the area under the curve. So we have an approximating Riemann sum where we have two partitions. Firstly, partition tau. We have for an interval from a to b, a partition into x0 to xn, so n plus 1 points, and n intervals. And for each of these intervals, we additionally pick a point yi that falls inside the interval, and that defines a second partition sigma n. Delta xi is the length of the ith interval, and with that the approximating sum for the area under the curve f is given by the sum of the length of the interval times the function evaluated at the intermediate point yi. So to graph this, suppose we have here the function. Let this be A and this B. So we are interested in the area under the curve. And we make a very rough approximation here with just x1, x2, x3, x4 and x5. So we have 6 intervals and 7 points. And additionally, we might take the midpoint of the interval. So that would be y1, y2, etc. up to y6. And then we measure the area under the curve by the sum of these rectangles, where the rectangle is over the interval and has height, the function evaluated at the midpoint of the interval. And as we let the intervals, the length of the intervals shrink, irrespectively of the points that we choose, we get one limit, which is called the Riemann integral. So the Riemann integral is defined as the limit, usually denoted in this form, as the limit of this Riemann approximating sum. And we assume, by saying the Riemann integral is defined in this way, that firstly a limit exists, and secondly that it is independent of the two partitions tau n and sigma n, so of the sequence of partitions, and that the partitions additionally satisfy that the maximum length of the intervals tends to 0. The Riemann integral exists if the function f, of which we want to determine the area under the curve, is continuous or at least piecewise continuous. So piecewise continuous is clear. We in principle can add for each piece over which the function is continuous. We can measure the area by a Riemann sum, and then in the limit by the Riemann integral, and then sum these. So that makes clear that with continuity we also have the Riemann integral existing for piecewise continuity. Next, in some applications we are not interested in exactly the area under the curve, but the value of the function is additionally weighted in some form. So instead of taking the length of the interval, we have some weight attributed to the interval, which is given by this function g. So we evaluate g at the point xi and subtract g at the point xi minus 1, which we, here this difference, this increment, we also denote by delta gxi. So such a sum is called a Riemann-Stieltjes sum, and it leads to the Riemann-Stieltjes integral, which is said to exist if the limit of these Riemann-Stieltjes sums exists and is independent of the partitions that are chosen here for the approximation, and if the maximum length or the length of the largest or longest interval tends to 0. The existence is a bit more complicated than in the Riemann case. So the two functions f and g must not have discontinuities at a common point. So they must have their discontinuities at different points from each other. And additionally, the function f must have bounded p variation and g must have bounded q variation for some values p and q being positive, such that 1 over p plus 1 over q is larger than 1. So bounded p variation means that, so for the function f, that we take a partition and we sum f at xi minus f at xi minus 1. We take the absolute value of this interval, or this increment in f, over the interval from xi minus 1 to xi, and we sum, and if this in the limit for n to infinity stays bounded, so stays finite, then we say that we have a bounded p variation, well, that is bounded 1 variation, and if we have p variation, then we require here the sum over the pth power of these increments. The same, of course, then for g. We have the same expression with f replaced by g, and additionally p replaced by q. Then we have the bounded q variation for g, and then the p and the q must satisfy this relationship, and then the Riemann-Stieltjes integral actually exists. If the function g is continuously differentiable with the derivative g of x, and additionally f of x is continuous, then actually the Riemann-Stieltjes integral exists, and it is given by the Riemann integral of the product of f and g. The Riemann-Stieltjes integral, however, is more general. So here we have a g being a continuous function, leading then, as it is the derivative of capital G, this implies that capital G is also a continuous function. The Riemann-Stieltjes integral allows more generally that the function g has jumps. So that means that single points at which the function g has jumps have a particular weight, so the weight is attributed to points in addition to being also allocated to intervals if the increment over such an interval is positive. As an example, we can consider a Poisson process, so let Nt be a Poisson process. Recall that a Poisson process, for a Poisson process, n of t is usually thought as the number of events that have occurred up to time t. And so it's an integer valued stochastic process, which is piecewise constant between jumps. And the number of events is Poisson distributed. In addition, the process has stationary and independent increments, which is of no relevance here for this example. Additionally, let f be a continuous function. Then we can define the Riemann-Stieltjes integral of f with respect to dnt, which becomes the sum of the function f evaluated at the points tau I, which are the occurrence of events in the interval from 0 to t. And n of t is the Poisson distributed number of events in that interval. So tau I are exactly the jump points of the Poisson process here. Now we are interested in applying integrals to the Brownian motion. So for instance, we might be interested in the integral of the Brownian motion in the form of a Riemann integral. So there's no problem with that, as the Brownian motion is a continuous function, has almost surely continuous sample paths. This integral can be defined almost surely, so for each sample path, or say almost all sample paths to be correct. Similarly, if we have, for instance, differentiable function f, then since b is continuous, the Riemann-Stieltjes integral of f with respect to b also exists. But more interestingly, we are interested here also in the integral of Brownian motion with respect to the Brownian motion, same Brownian motion. So integral bs dbs. And that is unclear, so it is clearly not a Riemann integral, as we have here the weight for the intervals, so not a ds. But it is also cannot be interpreted as a Riemann-Stieltjes integral, as the assumptions or conditions for the Riemann-Stieltjes integral are not met by this expression. So it can be actually shown that the Brownian motion has a bounded p variation for p being larger than 2. So, as said before, we take the supremum over all partitions of length n and the supremum of n to infinity of the absolute p powers of the increments of the Brownian motion. And that is finite if p is larger than 2, but it is infinite if p is larger or equal to. So that means, as we have here the same Brownian motion as an integrand and an integrator, we have 1 over p plus 1 over p, that is 2 over p, as a condition, and as p is larger than 2, we actually have here that 2 over p is not larger than 1 for in the case of the Brownell motion, so the condition for the existence of the Riemann-Stieltjes integral is not met. So this integral here, if we can attribute any sense to it, this particular formula, definitely it cannot be interpreted as a Riemann-Stieltjes integral. So let's have a look at the quadratic variation. So that is the point where we get in trouble with the Brownell motion. So as said, for any higher power this will stay finite, but for the quadratic variation it is actually not finite. So to understand that, as it might seem surprising actually that this does not exist, we can show that actually for every nested sequence of partitions, so that means if we have points in the partition tau n, so x0 to xn, then for the next partition at any higher n, the same points are reused, with of course then additionally points to form a new finer partition. So all points from previous steps are reused at later steps in the sequence. Additionally, we assume that the length of the intervals is going down to 0. Then actually it can be shown that for such nested sequences the quadratic variation, so we take the square of the increment over such intervals and sum it up, then it almost surely, so for almost all outcomes in the sample space, converges to t. If we take here the increments only up to time t. So that seems as if actually the quadratic variation would exist. However, this is for a particular sequence of partitions, namely nested sequences. And in contrast to this result, one can also show that for almost every sample path of the Brownell motion, there exists a worst-case sequence tau n of partitions, such that the quadratic variation limit tends to infinity. So in that sense, such a sequence would be the worst-case scenario, where the quadratic length of the increments actually tends to infinity. And that is true for almost every sample path. So what the problem here is, that the union of null sets is not a null set, as we have uncountably many sample paths. So for each sample path we have a worst case scenario which has probability 0, as has every sample path. However, here in this formula for the quadratic variation, we look at the supremum over all partitions. So for every sample path in here, so if we evaluate that for a particular sample path, we can actually here in the supremum have to consider the worst case partition, for which this then tends to infinity, for n to infinity. So even so, we have a lot of null sets. As we have uncountably many sample paths, the union of all these null sets actually form the complete sample space, or almost the complete sample space up to a null set. So the second remark here in the conclusion is what we already said, that for almost every sample path there exists a worst case sequence of partition for which the sum of the squared increments does not converge. So have a closer look at the approximating Riemann-Stieltjes sum for this integral b dbs. So we here take a particular choice of evaluation of the integrand, namely we take the left endpoint. We will actually see that which point in the interval we take actually matters very much, and for reasons that become later obvious, we are interested in taking here the left endpoint. So this increment here is in the future to this evaluation point of the integrand. So with a little bit of algebra, we can transform this Riemann-Stieltjes sum into this expression. So what we have here is a mixed term and a quadratic term at time ti minus 1 with a negative sign. So here we put this, we split that in half parts. So one half is here in this first sum, and the other half is with this minus in here. So these two terms become this here. Furthermore, this mixed term is exactly this term here. And in order to extend these two terms here into a binomial formula, which then gives bti minus 1 in brackets squared, we have to subtract also the second power of b at time ti. So we subtract it and add it. So here we have now two terms, namely here the difference of the squares, and here the square of the difference. These first sums, as we have two single terms, each squared, with alternating sign, so the first one is plus, the second is minus, and is one time step earlier than this point. Now for the previous interval, this point becomes the upper part or upper end of the interval and has a positive part. So these terms cancel out. So actually we have a starting from bt1 square minus b0 is actually 0 square. Then we have for the next bt2 square minus bt1 square, and exactly these two terms cancel out. And then we have, of course, bt3 square minus bt2 square, so again, two cancel out. So at the end, we obtain the largest value, so that is bt square at capital T, minus the smallest value, which is 0 square, or simply can be dropped. So in total, this sum here times a half gives us a half b square at capital T. For the other term here, this, as I said, that is by construction second binomial formula, so we can write it as the increment squared and summed times a half. So that here is the quadratic variation, and this term is why we cannot actually make, at least almost surely, so pathwise, sense of this approximating Riemann-Stieltjes sums, as this here does not converge almost surely, so for all sample paths. Actually, it does not converge for almost all sample paths if we consider arbitrary partitions. However, we can show that this quadratic variation part converges in mean square. So we can show that the mean of this quadratic variation part very easily, as BTI, this increment is normally distributed with mean 0 and variance Ti minus Ti minus 1, so that is delta Ti. The mean of the squared increment actually is the variance of this increment, which is delta Ti. So we have the sum of all these intervals, which is the total length of the interval from 0 to t, so that is t. Likewise, we can show that the variance of the same expression, so we can write it, for instance, as the covariance of a double sum of the increments, and then evaluating that further, we find an upper bound which is 2 times the largest value of the delta Ti times t. So with that, these two conditions together are sufficient for the so-called mean square convergence. So the Riemann-Stieltjes sum that we are considering converges for n to infinity in mean square to the expression a half bt square minus capital T. And this mean square limit of this sum will then also be denoted as the integral of bt dbt, which is the stochastic integral. So it should be noted here from the construction that even so we used the traditional notation with an integral, this here is not a traditional integral area under the curve of this function with weightings according to the same Brownian motion. So this integral is not pathwise defined, but it is in a mean square sense defined as a limiting a random variable. So that makes it, of course, very different from ordinary integration theory to work with the stochastic integral. Now, this is a very special case. We will see that we rarely can evaluate the stochastic integrals explicitly, but we can derive a number of properties, which we will do later in the session. So instead, the question is, how can we define the limiting sum or this stochastic integral in case where we cannot do such explicit derivations as in the case of this eta stochastic integral Vt dVt. So we do that as often in integration theory by approximating process. So instead of considering first general functions, we first consider so-called simple processes C, which are piecewise constant processes. So we have a process on the interval from 0 to t, which is the interval over which we want to define the eta stochastic integral, and Ct is a process on that interval which is piecewise constant. So on the interval from ti to ti plus 1, it takes the value xi, where xi is a random variable with existing variance or second moment, and additionally xi is supposed to be fti measurable. So at the left endpoint of this interval, this random variable is actually known. So for such simple processes, we can simply define the eta stochastic integral, denoted as ITC, or more formally as the integral of Cs dvs, as the sum of the xi's times the increment of the Brownian motion over the interval from ti to ti plus 1. So here we use this notation, which is the minimum of ti plus 1 and t, to cut the summation at time t, and hence to define here a stochastic process indexed by time t. More formally, we can write, more directly, we can write this sum also as the first n-1 terms, and then assuming that t is larger than tm but smaller than tm plus 1, we have the last term xm times the increment over the interval from tm to time t, which is the index time here. Defining the stochastic integral in this form, we can immediately see that we have continuous sample paths. So that is due to continuity of the sample paths of the Brownian motion. So here we have the increment of the Brownian motion, which for t increases in a continuous fashion, and at a new point, so once we have here t at time tm plus 1, we get a new term here for the xm plus 1 times the length of the next increment, and that, however, starts again smoothly with 0 and then slowly increasing to its maximal length. So that shows continuity of the sample paths of the stochastic integral here. Then also it's clear by this representation here that it only involves increments up to time t, and also random variables that are measurable at time t. So this means that this process ITC is adapted to the natural filtration of the underlying Brownian motion. More importantly, we have a martingale property with respect to the same filtration. We will see that in the next slide. And from that, we will see that actually the mean of this integral equals 0, because having the martingale property, the mean here of I, this integral at time t, actually equals the mean of the integral at time 0, which is a sum from 0 to 0 and therefore 0. So due to the continuous sample pattern that we have, then the variance, which is equal to the second moment as the mean is 0, can be also simply expressed by the integral of the expectation of the underlying simple process, the second moment of this process, which can be then written in terms of the underlying random variables xi. So we have the moments of these multiplied by the length of the intervals summed. And this is called the isometry property, as actually this here can be seen as a norm on the function space of, so here in this case, of all simple functions on the interval 0 t, so piecewise constant functions on the interval 0 t. And this here can be seen as a norm on the space of stochastic processes, and the two norms actually living in different function spaces actually are equal, so that is called the isometry property. Now coming to the martingale property, so let's assume that S is a time point between tk and tk plus 1, and t is between time tm and tm plus 1. So we can write our integral itc in the following way. So we have the first k min or k summons here, xi times increment over the next interval, plus then the first part of the interval from tk to s, so we have xk times the increment from tk to bs, plus the same xi at xk times the remaining increment for the remaining interval. Then we have the next few terms until we have the final term, as we are looking at time t, which is larger than tm but smaller than tm plus 1. We only look at the increment from time tm to time t multiplied by xm. Now we can evaluate conditional expectation given fs. So as this is completely known given the information that we have at time s, this stays fixed. This here also stays fixed, as this is an increment being known at time s. In contrast, here we have a random variable being known at time s, while the remaining increment here is not known and is independent from all that information earlier. So the mean of these two parts becomes the mean of xk times the mean of the increment, where the later is actually 0, so this term vanishes. Similarly, all these terms here vanish as well, as we can, if we take the mean of xi times this increment, we simply replace the mean by the mean of the conditional mean given time ti, and in that case xi becomes ti measurable, therefore can be put out, and we are left with the conditional expectation of this increment given the information we have at time ti. However, this increment is independent of the past, so its condition mean equals its mean equals 0. So all these terms also vanish, and finally same argument. If we are interested in the conditional mean of this part, we can simply replace by the law of iterated expectation the conditional expectation by the conditional expectation of the conditional expectation of this here given time t, or time tm. Then these two parts become known, while this increment again is independent of the information that we have, and its mean becomes 0. So that is shown here. So we keep the first two parts terms, and all other terms are 0. So these two terms, however, are exactly this process I of c at time point s. So this shows the martingale property for this integral. Now if we want to generalize this to general processes, so we consider based on this observation, so that the second moment of this stochastic process can be written in this form, that we integrate over the second moment of the underlying function. We can actually take that as a defining element and then define the eta stochastic integral for all functions c for which this expression stays finite and ct is adapted with respect to the Brownian motion sigma, or filtration of the Brownian motion. So we have this space which is L2 space in the sense that we look here at second moments. Then we have two simple results. Firstly, such a process here, CT, can be approximated by a sequence of simple functions. So we have simple functions Cn, for which we already defined the integral, and these become close or converge to C in this following mean square sense. So we have the difference between the limit and the functions, absolute value square integrated, and then, as we have here random variables, taken the mean of, and we can find here a sequence of simple functions such that this here converges to 0. So that means that rather looking at arbitrary general functions Ct, we can look at an approximating sequence of simple functions or simple processes for which we already defined the integral. Now fact 2 says that with the definition of such a C here, there exists a process IC on the interval from 0 to t, such that the mean of the largest deviation of this stochastic integral defined for the simple process Cn, and the stochastic integral or the process that is given here at the limit, that this expression here converges to 0. So that means instead of defining this eta stochastic integral directly, we use approximating sequences that approximate the integrand of interest ct, and by this result here we can use the same sequence and let it tend to infinity, so that here we have actually then that the resulting integral arbitrary well also over all time points t approximates this limiting integral. So this mean square limit that is given here in this expression called IC is the stochastic integral of the function c, and we again more commonly use the notation integral of c as dbs for all t in the interval of interest from 0 to capital T. So that means that this function of integrals converges to a process in mean square. And this mean square limit is then called the stochastic integral. Now, as we define the stochastic integral for a general function as the limit obtained from simple processes, or stochastic integrals for simple processes for which we already have properties, the properties simply carry over to the general case. So in particular, this integral of the function c is a martingale with respect to the natural filtration. It has also continuous sample paths, it has mean zero, and the variance is given by this expression, so the integral over the second moment of the function cs. Now, before we continue next week with the stochastic differential equations and the Ito formula, so go in the direction of financial applications as discussed in the track on actuarial science. We now have a look at an application of the theory in the time series context. So we consider a discrete time random walk given by this formula, so xt equals the value of the process at the previous point in time t-1 plus some noise. So we have what we call a random walk or an autoregressive process degenerated as here the coefficient does not fulfill the stationarity assumption. So further we assume that the innovation process epsilon t is a sequence of independent identically distributed random variables with mean zero and variance sigma square. Now if we have data on this process, we might actually fit an AR1 model to the data, and then we could test whether alpha equals 1 or not in order to find out whether we actually have a random walk or a stationary process. Now, as we have here a simple regression equation, we can simply calculate the ordinary least squares estimator of the parameter alpha, which is an empirical cross covariance of xt with x at a one step back, xt minus 1, and divided by the sum of the xt minus 1 square. Now the question is, what is the asymptotic distribution of alpha? Now, instead of alpha, we will look at actually alpha minus 1. So we look at alpha hat minus 1, and that is xt minus 1 times xt minus xt minus 1 square divided by the sum of xt minus 1 squared. Okay, and this under the null hypothesis, so that we have a random walk, can be written as xt minus 1. Okay, so here we have simply a sum of xt minus 1 square, and noting that xt itself is a random walk, so under the null hypothesis H0, where alpha actually equals 1, we have that xt minus 1 can be written as the sum of the epsilon i's, and the epsilon i's are independent, identically distributed with mean 0 and variance sigma square. So this implies that here for this xt minus 1 we can, after proper standardization, apply the functional central limit theorem to show that this sum here converges to a Brownian motion. So we have divided by square root capital T which we define as the process. So here that would be actually up to time t minus 1, so that would be the process at time t minus 1 over t at n, where actually n equals t over delta t. Okay, which is delta t is 1, so that is t. So actually you can simply put t here. So this converges by the functional central limit theorem in distribution to a Brownian motion. So that's the first part. Now here we need, in order to show that this here converges, we now need to express this, for instance, as a continuous function of xt minus 1. So we have So what we have here is the partial sum process here. We take squares and sums. Now this here can be expressed in terms of the process y at time t minus 1 over t. So actually it should be that has never been really clarified here in the formulas. As we have capital T observations, the observations run from time t to capital T, and same should be here actually. Up to T. So here that is correct. Now this process here that we have here is actually defined constantly over the interval, and in the form that it is defined, it's piecewise constant on the interval from time ti minus 1 over t to t over t. So what we have here is the value of the function over the interval times the length of the interval and then summed. So actually to show that, if you have here such a piecewise function, then the area under the curve of this function is actually the sum of all these blocks, and the blocks have each width 1 over t and the height y t minus 1 over t, y at t minus 2 over t, etc. Okay, so that is for simply yt. Now here we are looking actually at the square of the same process that only changes second power. So what we are interested in here, or what we have by having here 1 over t times the function value, is actually the area under the curve, which actually is given by the ordinary Riemann integral from 0 to t of y at tau d square d tau. So we have the function of interest at t squared integrated. And these two expressions are exactly equal because of the piecewise constancy of this function here, as depicted here. So that means this here actually is a continuous function, as the integral of a integrand is continuous in the integrand. That is a constant function of this stochastic process. Yes. Which implies by the continuous mapping theorem that g of yt converges to the function of the Brownian motion, which is the integral from 0 to t of the Brownian motion tau d tau. Okay, so and sorry, again, as the function here is the process square, actually this should be here square. So that is the limit for this expression, and we have a 1 over t squared added into the denominator. And for the numerator we have to show that either we use the same or different factor, and then we can see what is the rate of convergence of this function here, alpha hat, this estimator. So next we have to look at we do that on the next slide, on the sum of cti minus 1 times ct minus xt minus 1, where t ranges from 1 to capital T. Now we can show in similar fashion. So if we multiply by 1 over t, that we have everything expressed in terms of x divided by square root capital T, which actually can be written as so we have here in terms of y, the process at time t minus 1 over t times the increment and in the same form as we calculated here sums as such a sum for the Brownian motion, we can now do it for this process here, and show that this becomes then a half y1 t minus a half sum of and then the increment square So by the continuous mapping theorem, again, function essential limit theorem implies that y converges to a Brownian motion, and correspondingly this first term converges in distribution to a half b1 at capital T, b1. Actually that is square. This process here is also a square. And the second part here these are actually the epsilons. So that is actually here epsilon t squared. So what we have is the sum of the epsilon t squares over t. So that is actually the sample mean of this here is the sample mean of the epsilon t squares, which means it converges by the weak law of large numbers in probability and hence in distribution to the expectation of epsilon t square, which is 1, or in the more general case, if it is sigma, then here in the boundary motion we also have a factor sigma. So for the moment we show it only for sigma equals 1. So we have minus a half. And those which actually is equal to the e to stochastic integral from 0 to 1 of pt dbt. That is exactly the mean square limit of the approximating Riemann-Stieltjes sum, as we have shown, which is defined then as the e to stochastic integral here. So this implies, important, here we actually only required 1 over t. For the denominator we actually required a factor 1 over t squared, which means that our statistic here needs to be multiplied by minus 1, by capital T. So it converges in probability to 0 with a rate of 1 over t, and only after multiplying by capital T it converges to a non-degenerate distribution. And so we have convergence in distribution to either writing it this way, so a half b1 square minus a half over the integral from 0 to 1 of bt squared dt, or equivalently as the Riemann-Stieltjes integral, not the e to stochastic integral, divided by this ordinary Riemann integral. So that means this random variable asymptotically has the same distribution as this transformation of a boundary